Yay! That's it, isn't it? Okay. So this is a coded data question. We've got some for n values. So for n values of the variable x, it's given, and we've got this data here. Okay, and we've got to find the value of n. Okay, now this one here means that we've added up all of the x values, but for each x value, we've taken away 200. In other words, we've taken away 200 n times, and this is just adding up all of the x values. So here's how I'm thinking about it. If we take this one, and then we take away 200 times n, because we're taking that 200 away for every value of x, and there's n values of x, that ought to give us the 446. So when we plug this in, what do we get for our n value there? I was getting 32, is that correct? Yeah. Nice. So that's quite a good one. Remember when you guys were scared of coded data? No more, eh? Okay. This time, this is a... Okay, what type of question have we got here? We can identify it just by looking at it. What do you think? Yeah, discrete random variables. Okay, so probability distribution table. We're summing the dice. So what's the smallest value of x that we can get? 2. Yeah, 1 and 1, so 2. And what other values can we get there? What do you say there, Kenny? Yeah, 2, 3, 4, 5, 6. And then on this part, we'll have the probability. You've got rulers. I won't embarrass myself by doing too many lines. Okay, what is the chance of getting a 2? Well, how many ways can we get a 2? Well, the first dice is a 1/6 chance, and the second one has a 1/6 chance. So it should be 1/36. Now, if we think about 3s, what are the different ways that we can get a 3? We could get a 1 the first time and then a 2. Or we could get a 2 the first time and then a 1. Now, what's the chance of getting a 1 and then a 2? 1/6 times Ruth. Yep, 2/6. Whoops, yep, 2/6. And so we could actually just do this and then times it by 2. So altogether, that should give us 1/9, because we get 2/36, which is 1/18, and we times that by 2, which is 1/9. Okay, now what ways can we get a 4? We could get 1 and 3, or we could get 3 and 1, or we could get 2 and 2. So 1 and 3 would be, what would 1 and 3 be? So 1/6 times what, you reckon, Ruth? Yeah, okay, cool. I'm going to do half. And then we can times that by 2. Why am I timesing it by 2? Because I could also get it the 3 first, then the 1. And then what about getting a 2 and a 2? Who can help me with that? What do you reckon, Rihanna? Yeah. So I'm going to just do 1/3 squared if that's okay. And then we add all of that together. What do we get when we add it all together? What have you got there? 5/18. Yeah, I got that too. All right, now 5. So how are we going to get 5s? I guess we could go 2 and 3, or 3 and 2. So we could simplify that by going 2 lots of, now what's a 2? 1/3, and then a 3 is 1/2. So it should be 1/3, I think. Okay, and 6 should be easy. The only way to get 6 is 3, 3, and that's 1/2 times 1/2, so it should just be simply 1/4. So it's those middle ones that you've just got to worry about there. Now, we've got to find EX and VRX in the next question. So let's just work on EX first. I'm going to do it here so I can keep it on the same screen. So it should be 2 lots of 1/36 plus 3 lots of 1/9 plus 4 lots of 5/18 plus 5 lots of 1/3 plus 6 lots of 1/4. I'm getting 14/3. Yep. All right, and then we're doing VRX. So this one, we're going to go, we square the x values. So 2 squared times that by 1/36 plus 3 squared times 1/9 plus 4 squared times 5/18 plus 5 squared times 1/3 plus 6 squared times 1/4. And then what do we do with that? We pop that all over 36. There it is. Minus 14/3. And we're going to square that. Okay, what does that actually give us? 10/9. Okay. Yep. Which is 1.1, isn't it? Okay, yeah, that's cool. All right. Okay, now I think we can probably skip number 3 because I think we know how to do that. I think we know how to do box and whisker graphs. When you're doing, the only thing I just want to make a comment on is when you're making a comparison between diameters of the pipes, make sure it always asks you to do this in context. So don't go, A is more varied than B. You need to say the diameters of the pipes in A are more varied than those in B. So make it contextual, or the pipes in A have a larger diameter, or their diameter is more spread out. Okay, so make sure you're referring back to the question and not just saying a general statement. That's probably important. Okay, let's move on. Okay, yeah, this is a good one to do. So we've got, this is normal distribution, because we've got this in here. Okay, so what is this 2.02 meaning, Bethany? Good. And the standard deviation is therefore 0.03. Okay, variance is 0.03 squared. We've got to find the probability that a randomly chosen bag of rice produced by Edwards weighs between 1.98 and 2.03. So we're going to call this Z1. We're going to find a Z1 for that, and we're going to find Z2 for this. Okay, so Z1 equals, we're going to pop that 1.98, subtract the 2.02, which is our mean, and we pop that over our standard deviation, which is 0.03. So this will give us a negative Z value. shout it out if you get it. Yep, with the 12.3 recurring. I agree. Perfect. Let's do Z2 while we're at it. And here we've got 2.03 minus 2.02 all over 0.03. Who's got a Z number for that? 0.3 recurring. Okay, now we're trying to find the chance that it lies between those. So what we're trying to find is the probability that minus 1.3 recurring is less than Z, which is less than 0.3 recurring. Or if we were to sketch the normal distribution curve, here's our mean, here's Z2, here's Z1, and we're wanting the shaded area. Okay, so we're wanting all of that. Now, the next step is to write that in terms of phi. So how do we get everything under 0.3? Well, that would be phi. So this is equal to phi 0.333 take away. Now we've got to get rid of this bottom bit here. So how do we define this bit here, this green bit? Because that's the bit that we've got to get rid of, because currently we've got everything below this point here. So how can we define that green bit? Yes. Very good. You're a genius. Okay, so let's use our Z tables now and see if we can come up with some numbers for that. Is everyone getting 0.6304 for 0.3 recurring? And then that 1.33. Let's have a look. 1.33, and then we add on. Is it 5 to the end? 0.9087. I think it should be 0.9087. And when we plug that all in, getting 0.5391. Is that correct? Is everyone happy with that? Nice. Okay, moving on. The weights of bags produced by binders. Who's binders? Must be a different company or something. Normally distributed with mean of blah, standard deviation of blah, a random sample of 5,000 of these bags, 134 weighed more than 2.6. Okay, so we want to find out the percentage of them that weigh less than 2.6. Why do I want to do less? Well, because the Z numbers give you the percentage that's less, so I think it's easier for us to work out that way. So what we're going to do is we're going to go 5,000 is our denominator. We're going to do 5,000, take away the 134 that weigh more than 2.6, and then we're going to times this whole thing by 100 to find out the percentage that weigh less than that, okay? Who's got a percentage for that? Okay, yeah, so 97.32% way less than that. So what we're talking about is, oh, it's dodgy. Okay, so here's our mean. And if it's 97%, it's like way out here. So we've got to find the Z number for 0.9732. So we're going to go to our table and find out what that could be. 9732. 97. Here's a 9. Oh, look. Huh. It's right there. We don't have to do any silly adding or anything. So it's 1.93. Is everyone okay with that? That's making sense. 1.93. Nice. So Z equals 1.93. Now we can plug this into our equation. So 1.93 is equal to 2.6, which is the value where 97% is lower than it. Subtract our mean, which is 2.55, and then we're going to divide that by the standard deviation, which we don't know, and so we can do some rearrangement to find out what standard deviation is. I'm getting 0.0259 for this to 3 sig figures. Perfect. Okay. Just have a quick read of this question and determine what you think we are dealing with. What topic? Binomials? Everyone okay with binomials? Yeah, it is. Okay. 28% don't play any musical instrument. 52 play exactly one musical instrument, and the remainder play to me would be in the remainder in this case. Okay. A sample of 12 students is chosen, and we've got to find the probability that more than 9 of these students play at least one musical instrument. So let's find out percentage greater than or equal to one instrument. What is that? 52. Oh, I guess we just go 100 take away 28, hey? Cool. So, where's my cursor gone? Okay. Very good. And so that's the probability of success when we're selecting these. We want more than 9 of these students play at least one instrument. So we could do, I think we're just going to go 10, choose, oh, sorry, 12, choose 10, because there's 12 students. 12, choose 10, times the probability of success, which is 72%, so 0.72. We've got 10 of them. And then the failures, failure management, 0.28 squared. Okay, next one is, this time we've got 11, and that will be 0.72 to 11 and 0.28. And then if we have all 12 of these students playing at least one instrument, that will be 0.72 to the 12, and obviously 0.28 would be to the 0, so we could actually just leave it up. Now, I've noticed when I look at the mark schemes that they like you to write out the individual probabilities for these as one of the method marks, so let's not lose a mark there. So the first one is 0.193725, so write it down. The second one is 0.0905725 or something. The last one is 0.0194081. So that is worth a mark, having the individual probabilities written down for method. And then add it all up and do your final answer to 3 sig figures. and I'm getting 0.304, but correct me if I'm wrong. That's good. Okay. Now this time we're sampling 90 students, and we've got to use an approximation to find the probability that exactly one, fewer than 40 play exactly one musical instrument. So what is the probability of exactly one musical instrument? 52%. Okay, so it's a different percentage now. Okay, so we're going to say this is a binomial, and there are 90 students, so 90 trials, and the probability of success is 0.52. Now it says we're using an approximation, so this is normal approximation. So we're going to change our to y is normally distributed. And how do we get the mean? What are we going to do here? Ruth, do you remember? Yeah, 90 times 0.52 gives us 46.8. And how do we get the variance? What are we going to do next, Sonia? Yeah. What does that give us? Is it 20? I think my handwriting says 22.464 here. Okay, now that's variance. Don't forget that we're going to square root it when we're trying to find z values and stuff. Okay, now we want the probability that y fewer than 40. So we've got to do something very important at this point in time. Don't forget, we need to do a continuity correction. So we want less than 40. So when we change this to normal, it's got to be less than 39.5. All right. Okay. Now, what we're going to do next is we're going to find a z value for 39.5. So z equals 39.5, take away our mean, which is 46.8, divided by our standard deviation, which is square root 22.464. Excuse me. We're getting negative 1.540. No? We are. Okay, nice. And we want the probability that fewer than that. So I'm just going to do a little sketch now. Here's my normal distribution. Here's my mean. And I know that 1.5 is negative 1.5 is out here, and I want this bit here. So the probability that z is less than negative 1.540 equals, who can tell me? Yep. Yep. 1 minus phi 1.540, and we're going to need to look that up. Let's have a look. Where is it? Oh, not that one. 1.540. 1.54. Is it 9382? I'm getting 9382. One minus 0.9382, and when we chuck this into calculator or our heads, 0.0618 is our answer there. Now we come to the moment that you've all been waiting for. All right, well, the first one's okay, isn't it? We've got to arrange the 9 letters in the word crocodile. So there's 9 letters, so it's 9 factorial. We do a quick check. Are there any duplicates? I think we've got a couple of C's. We've got a couple of O's. And that's it. 90,720 should be the answer. Is that all right, Bethany? You happy? Okay. Now the next one is we've got to find the the different arrangements of the 9 letters in the word crocodile, which there is a C at the end and the O's are not together. Oh, at each end. Okay, so it's like this. 1, and then we've got 1, 2, 3, 4, 5, 6, 7, and we've got C at the other end. So we want to find the ways that the 2 O's are not together. So what we're going to do is we're going to find the total ways, then the ways that the O's are together, and subtract the ways the O's are together from the total ways. So that's our strategy for these. Total arrangements, subtract ways O's are together. That's my strategy for this. Total arrangements. We're arranging 7 letters, so it's 7 factorial. Do we have duplicates? Yes, we've got 2 O's. So, for instance, if you had an O here and an O here, that's one arrangement. Even if you swap the O's over, it would still be the same because they're duplicates. So we're ignoring those. Goodbye. Okay, right. So that should be that one. Now, what about the ways that we join the O's together? Well, if we put the O's together, we can kind of treat them like a block. So imagine this. It becomes like one letter, doesn't it? Yeah. So then it would just be 6 factorial for the other letters. And you can arrange those O's, you can stick them in those 6 factorial. Because you got 1, 2, 3, 4, 5, 6. It's part of the 6 factorials, and it doesn't matter if you switch the O's around because they're exactly the same. So 7 factorial over 2 factorial take by 6 factorial gives me 1800 or 1800. All right. Now, this time we're going to select letters from crocodile. And we're going to find the number of selections in which the number of C's is not the same as the number of O's. Okay, so what are the ways we could do this? Well, we could get 1 C and no O's. We could get 1 C and 2 O's. We could get 2 C's and no O's. We could get, what else could we get? We could go 1 O and no C's. What else could we do? Anyone got some other ideas here? 2 C's and 1 O. 2 O's and a C. Whoops. We've done that one, haven't we? Yes. 2 O's and nothing. Yeah, okay. Now, let's look at the different ways that we can get this. So, if we're going to get this one here, the first one, 1 C and no O's, then you're selecting from, let's just highlight these letters. This one, where are we? This one, this one, this one, this one. Okay, so you can see there's 5 different letters we can choose from, and we're choosing 3 of them. So that would be 5 choose 3, which is 10. Now, the next one is we've got 1 selection to make, and we're choosing it from 5 letters that aren't C or O, so that would be 5 choose 1, which of course is 5. the next one, we've got 5 letters to choose from, and we're choosing 2. So it's 5 choose 2, which is again 10. The next one is 1O, and we've got 3 letters to fill, and we're choosing them from the non-C's and non-O, so that's 5 choose 3, which is 10. The next one, we've got our C's, we've got our O's, and we've got to choose something that's not an O. There's only 5 of them, and we've got to choose 1, so it's 5 choose 1. And then finally, we're choosing from the 5, and we're choosing 2. 5 choose 2, so 10. So we add these all up to get our total. 10, 20, 30, 40, 50. It should be 50. Good. Okay, moving on. Find the number of ways in which 9 letters in the word crocodile can be divided into 3 groups, each containing 3 letters. Oh. If the 2 C's must be in different groups. Okay, so again, I think we're just going to draw out some of these different options here. So we could do, the way we're going to think about it is we'll put in our O's because that makes life a bit easier. So we could do it like this: C-O-O, C something something, and then something something something. That's one way of doing it. Or we could divide the O's up like this, right? Or we could have it so that the C's are without O's, and the O's must therefore be in the remaining group. Alternatively, we might have the O's in with one of the C's, the other C being O-less, and then the final group having one O. Those are the different ways of arranging the O's. Okay. Oh, I think this is the hardest one out of all of them. Okay, so how are we going to do this? Well, remember, let's cross out the letters that we've taken care of. Okay, so now you can see we've got those 5 letters again. Okay, so how many ways can we arrange, can we separate these letters out? Well, 5 choose 2 or 5 choose 3, which is exactly the same, right? If we put 5 choose 2, that would mean we're thinking about putting these ones in here. And then once you've put those in, there's no other options. The other 3 must go in the other one. Or you could go 5 choose 3 and fill in the group of 3 over here. And then there's no other options for the last 2. So either way, you get the same answer. So 5 choose 2, which is 10. Now the next one's a little bit more tricksy. You're going to go 5 choose 1. So you can put 1 in there, and then the next one is 4 choose 1. But then you're going to divide that by 2. Why am I dividing it by 2? I don't know, just because it looks good. Because we've got that repeat CO, CO. No. Or what's another way we could do it? We just do 5 choose 3. The next one is easier. So we could start off with the first C. We could go 5 choose 3. 5 choose 2. And then we've placed here and here, which means we've got only 3 letters left. So then we go 3, choose 2, and then the last letter has to go in the last spot. So that's, oh, this one's 10. This one is, what is that? 30. 30. Final one. I'm going to go 5, choose 2, and place in my. I'm going to place them first in here. Yeah, sometimes it's the same thing doing it depending on where you started. It will give you the same thing. 5, choose 2. I'm going to pop them there, and then I've only got 3 letters left to place. So I could either go 3, choose 1, or 3, choose 2. I'm going to do 3, choose 2. And that's exactly what I got for the previous one as well, isn't it? So 30. So the total is equal to 30 plus 30 plus 20, which is 80. So I think that was probably the hardest one out of all of that group. Okay, the next one's, what have we got here? This is probability, the probability section. Hannah buys 12 hollow chocolate eggs that each contain a sweet. The eggs look identical, but Hannah knows that 3 contain a red sweet, 4 contain an orange sweet, 5 contain a yellow sweet. Each of Hannah's 3 children, in turn, randomly chooses and eats one of the eggs, keeping the sweet it contained. Find the probability that all 3 eggs chosen contain the same color sweet. Okay, well, let's think about red, red, red. That's one way of doing it, isn't it? What's the chance of getting a red the first hollow chocolate egg you choose? Well, there are 12 chocolate eggs and there are 3 red sweets, so it would be 3/12. Then once you've eaten that one, now there are only 11 to choose from. How many of them are red? 2. And then now you want to choose your third. There's only 10 eggs left, and the chance of getting a red is now at that point 1. So when we multiply these all out, what do we get? Is it, I got 1 over 220. Yep. Now we're going to do the same with orange, orange, orange. Orange, orange, orange. Okay, so the first chance of getting an orange is 4 because there's 4 that have oranges, so it's 4/12. And then obviously each time we drop down 1, just as we did in the first case. So 4/12 times 3 11ths times 2 10ths. So this should be, and I got 1/55th, that one. And yellow, yellow, yellow follows the same pattern of logic. You've got 5 of them to start off with, so it's 5/12 times 4 11ths times 3 10ths, and this was giving me 1 over 22. The total, 22ths, is going to be the sum of those, and I get 3/44ths when I add them together. So that's my working there. Are you right with that? Is that okay? Yeah. All right. Next one is conditional probability. So find the probability that all 3 eggs contain yellow, given all 3 children have the same color sweet. Okay. So what we're doing here is we're trying to find the probability of 3 yellows intersection kids same color all over probability kids same color. Now, the previous question helps us somewhat. What's the probability of all 3 children having the same color suite. Oh, wait, sorry. Given that all 3 children have the same color suite, yeah. Okay, so yellows. What did we find for yellows? Was 1/22nd, I think. Yeah. And all 3 children have the same color suite. So what's the probability of that? Where's my cursor gone? There. 44th. Okay, and we can simplify this. Actually, we can do this in our heads, can't we? We can. Yes. Or you could have just changed this into 44th, but there we go. Yeah. Okay. Look, we're on the last question. This is our last question, is it? Oh, that's because it's easy. Okay. Find the probability that at least one of Hannah's 3 children chooses an egg that contains an orange sweet. Okay. So the way I would do this is, why don't we find 1 minus the probability of no oranges. Right? That's probably how I would do this. This is what I did. I did 8 choose 3, and then I did 12 choose 3. But I'm just having a bit of a brain fade about why I did that. Oh, are they only getting 1 sweet? Oh, I thought they were picking 3 sweets. Oh, well then it's totally like I was okay, right, overthinking this. What I've got is totally fine. I thought they had to pick 3 sweets, and now that's where we're running into trouble. Okay, fine, read jolly question. So if they're only picking 1 egg, there's 3 picks happening, and they've got to pick from the non-orange. Okay, so to pick from the non-orange is this bit here. There's 8 non-oranges, and we're choosing 3 of them. Okay, and then we're going to put that over the total number of choices you can make, which is 12 choose 3. And that's the probability that they don't pick an orange. But we want to find the probability that they choose at least, that there's at least 1 orange. So we just do 1 take away that. Okay, now I understand.